Welcome everybody to the second lecture of microwave engineering course. Today we'll be talking about transmission lines. It's mostly about its basics. So the transmission line theory is a theory that bridges the gap between field analysis and circuit theory. So it is some sort of like a transition in concept and tools and understanding between circuit theory and field analysis. The transmission line does have many different formats, as we're going to see shortly. And the main idea about the transmission line, or the main difference about the transmission line analysis, is that it is a distributed parameter network. So the voltage and current vary in magnitude and phase over the length of the transmission line. This doesn't happen in like circuit, like ordinary circuits, like lumped element circuits that we dealt with. The voltage and current on lumped element circuit is constant over each component. So the voltage on this resistance would be constant. While in microwave, the transmission line, the voltage and current would change on the same component along its dimension, as we're going to see. The transmission line can come in many different formats. Like one very famous transmission line is the coaxial waveguide, parallel plate transmission line. We have also like twisted pair transmission line, similar to the one used in like Ethernet cable. So those are sort of like cable kind of transmission line. We have also like printed circuit board transmission line, like the microstrip, strip line, coplanar waveguide, and many different kind of transmission line would like exist. We'll start our analysis by, okay, what is the model for the transmission line? How would we analyze and come up with the theory and connect the transmission line and study current and voltage on it? So historically speaking, when something new like appear in the scientific community, the first trial is try to model it based on the established theories or established body of knowledge. So at the time of introducing transmission line, what was there in like the scientific community? It was the circuit theory. So the first trial to analyze the transmission line was trying to put a lumped element model for the transmission line. So if we have like any kind of transmission line, let us assume we have parallel wire transmission line, we can model it physically as like some resistance in series with inductance, then some conductance in parallel with capacitance. So the resistance represent the like metallic along the direction of current flow. The inductance relates or like sort of like model the magnetic field generated by this like current flow. The conductance represents the losses that goes across the separation, the dielectric separating the two conductors, and the capacitance represent the capacitance between the two conductors of the transmission line. So any finite length of a transmission line can be divided into like shorter slices and cascade them, and we study like or analyze this transmission line in this form, in this way, cascaded sections of RLGC models. Of course, this is not how we analyze transmission line now, but this was like the very early model for the transmission line. Okay, so how would we do the analysis? So here, as we said, the voltage and current change across the dimension of the transmission line. So at this point, would have like, or we would denote the voltage as V of Z and T. At this section, it's V of Z plus delta Z and T. current at z plus delta z. So this is the z direction, and we would have like this resistance, inductance, capacitance, conductance. All of this are sort of like parameters per unit length. So the first thing to do the analysis, we apply Kirchhoff voltage law. We write the equation. We write Kirchhoff current law. We write the equation. So the voltage here at the input, or like the start of this segment, equal the voltage at this terminal plus some drop along those elements. So, or we can say the sum of the potential or the sum of voltage across the closed loop equal 0. So Vz minus the drop on R minus the drop on L minus the voltage here equal 0. We write Kirchhoff current law. The total current that goes into the node equal 0. So current in this segment and current out, the sum equal 0. So we can divide both equations by delta z and take the limit when delta z goes to 0. So dividing by delta z, and we will have partial z, so partial differentiation with respect to z, and we would have this form of the equation. If we assumed like sinusoidal steady state, or like if we assume like sinusoidal harmonics, as we talked in the introduction, this differentiation with respect to time would be like j omega. So the equation will look like this. The two equation now looks like this. Solving the two equations, we would get this like homogeneous differential equation of V as a function of Z with respect to Z, current as a function of Z with respect to Z, and this is a constant that equal this quantity here, and this is called complex propagation constant, and we're gonna see, or like we're gonna know shortly, why it is called propagation constant. And this propagation constant is a complex quantity. It's clear from its expression here, so we can express its real part as alpha and its imaginary part as beta. So solving this two equations, we would have like two solutions. So this is a second order linear differential equation. It does have like two solutions. One solution with minus gamma, one solution with plus gamma. And so this is the solution is e to the minus gamma z. The other solution e to the gamma z. And each like solution does have its own constant. So the general solution for the voltage would be certain constant for the first solution, e to the minus gamma z, plus a second constant for the second solution, e to the plus gamma z. And we're gonna shortly also know why we denote this negative or like minus, and we denote this positive. Same thing, same form of equation for current. The solution, the general solution for the current on the transmission line would be also like taking this format. So e to the minus gamma z, it represents a wave propagating in the positive z direction. This is why we just denote this constant with positive. E to the plus gamma z denotes a wave propagating in the negative z direction. So this is very similar to the plane wave in propagation in bounded media. So we also can show that the current is related to the voltage with this relation here. So we just need to pay attention. This is a negative sign, and this is sort of the complex impedance, which is the characteristic impedance of this transmission line. So this is the solution: a wave propagating in the positive z direction, another wave propagating in the negative z direction, and they have different weights or different constants. Their sum is the general solution. And how would we find those constants? In general, in electromagnetics, we find those constants from the boundary condition, as we're going to see. So this relation here, which is gamma, this expression divided by r to the j omega L, which is similar to this section. So we can say this is Z0, and we call it characteristic impedance, which is the relation between voltage and current. So voltage propagating in the positive direction and current propagating in the positive direction are related with Z0. The voltage propagating in negative Z and current propagating in negative Z are related by negative Z0. This sign is just because here we have e to the minus gamma Z, here we have e to the plus gamma Z, and this is the reason why we have different sign between the positive component of the wave, and positive means propagating in the positive Z direction, and negative means propagating in the negative Z direction. So in general, we can write the expression this way. We express the current in terms of volt in this format. And if we are, as we said, we can express the wave into multiple forms. If we would like to write the voltage as a real wave, we'll take the real component here and add the time dependency. We know that from previous, from Maxwell's equation, from the review in last lecture, we said that there is an implicit e to the j omega term here. If we take the real part of this expression, would have the real, or the amplitude of V naught plus cosine omega t minus beta z plus certain phase multiplied by e to the minus gamma z. So this, minus alpha z. And same or similar thing for the wave propagating in the negative direction. So for the positive z direction propagation, we have omega t minus beta z, very similar to the plane wave propagation in unbounded media. And for the wave propagating in the negative z direction, we have omega t minus beta z. And here we'll start to name this beta as the phase propagation constant, and alpha is the attenuation constant, because alpha represent here a decay in amplitude in the direction of propagation. So it's an attenuation constant. Here also it is an attenuation constant, even though it is positive, but z here is going in the negative direction. So the wave is propagating in the negative z direction. So when z is decaying, the wave is attenuating. So this is why alpha is the attenuation constant, beta is the phase constant. So again, as I said, the expression of the voltage wave and current wave on the transmission line are very similar to the wave equation in unbounded media. So from analogy, we can define the wavelength to equal 2 pi divided by beta, the phase velocity to equal omega divided by beta, and it's also equal lambda multiplied by f. So here I'm having like a recommended, so this changes the color. Okay, we have a recommended reading if you would like to read about like a different format for like the manipulations that we just did, but it is coming from the field theory. You can read this section of the book. Okay, lossless transmission line. So in many practical cases, the losses in the transmission line are very small and can be neglected. Losses neglection means we can neglect alpha, or we can say alpha equal 0, and gamma in this case will equal j beta, which is the phase constant. For this, like sort of like a very acceptable approximation that no losses means the conductor is perfect, so R equals 0. The dielectric is perfect, so there is no conductance, so J also equals 0. And we will lift up with gamma equal J omega L multiplied by J omega C, which equal J omega square root of LC. So which is J beta omega square root of LC. In this case, Z naught will be a constant, if we remember. So now Z naught equal J omega L divided by J omega C. R and J are set to 0. So we have square root of L over C, and it is a real quantity. So here also, like R is neglected, gamma is J beta, so we can find that Z naught in this case for lossless transmission line would be real quantity, and we can write the voltage equation as a positive constant, a constant for wave propagating in the positive Z direction, e to the minus J beta Z, because alpha equals 0, plus V minus wave propagating, the magnitude of wave propagating in the negative Z direction, multiplied by e to the J beta Z. The current would also have like a constant for the wave propagating in the positive Z, plus another constant for the wave propagating in the negative Z. And we can write current in terms of voltage this way. For the wave propagating in positive Z, the relation is I plus equal V naught plus divided by Z naught. For wave propagating in the negative Z direction, I minus equal V naught minus divided by Z naught multiplied by minus 1. So like just like carefully handle this. Don't like think this is negative. No, this is positive. It is negative when we express current in terms of voltage. So let us have this example. We have a 50 ohm lossless transmission line, and even if I didn't mention that it is lossless, if I give you the characteristic impedance as a real quantity, it means that it's lossless. So the voltage wave form does have this expression, and we would like to know what is the frequency of this signal, what is the phase velocity, what is the wavelength, what is the current waveform. So at this point, I would advise you to pause the video and try to solve this equation yourself. You can get back to previous parts of the video, or you can like look into the handout, try to solve this example by yourself, and then like resume the video. So now I'm going to assume that you are back like from pausing the video or trying it out yourself. So here V of Z does have this expression. So we know that it is sine or it's cosine omega t. So this is omega, which is 2 by f. So this term here is omega t. So we can get f to be 5.73 gigahertz. So minus beta z. So 24 is the beta. What we want is the phase velocity, which is omega over beta. So we can come up with the phase velocity, and you can see that the phase velocity is larger than the speed of light, because this is not the propagation velocity, this is the phase velocity. So we need to differentiate between them. So this is how fast the phase is varying, but it is not the speed of propagation of power or signal or anything. Lambda equal 2 pi over beta, so we can come up with lambda. For the expression of current, we know the current equals the voltage divided by Z naught or minus Z naught. We need to know if this wave is propagating in the positive direction or negative direction, and we know it from here. For positive direction, it is minus beta z, so we divide this by Z naught, which is 50 ohm, to come up with the expression for current. If the wave was propagating in the negative Z direction, there will be a negative sign here. So this is a wave propagating in the negative Z direction. Its relation to volt and current are related by minus Z naught. So if this is positive, there must be a negative sign here. So we need to pay attention to that. Okay, so now we'll go a little bit into circuits that use transmission line. So the transmission line is feeding certain load, that is ZL. We know the expression for the wave propagating in the positive Z direction. So the convention here is to assume Z equals 0 is at the load. So the wave is propagating this way, so this is the negative Z direction. So for a wave propagating in the positive Z direction, it does have this expression. If a wave is propagating in the negative Z direction, it would have this expression. And as I said, we choose Z equals 0 to be here. So how would we define or find the V naught plus and V naught minus? As I said also, it is through the boundary condition. What kind of boundary condition do we have here? The boundary conditions that we have here is VL, the total voltage at the load, is equal to the total current at the load multiplied by ZL. So this is from circuit theory. So the total current and total voltage must fulfill the boundary condition here, which is V equal IL. V at the load equal current in the load multiplied by ZL. And the Z is happening at Z equals 0. So the voltage, total voltage at the load, Z equals 0, does equal V naught plus V naught minus. Current equal I naught plus I naught minus, or if we express it in terms of voltage, it will be V plus over Z naught minus V minus over Z naught. The boundary condition, as I said, here is that V at the load equal I load multiplied by Z load. We write the equation, and this is the boundary condition here. And the boundary condition, just like rewriting it, would express the negative propagating magnitude to the positive propagating magnitude with this ratio, and this ratio V minus the reflected wave. So when we come to the load, so a wave propagating in the forward direction, the wave propagating in the negative Z is called a wave propagating in the reverse direction. So when the wave propagating in the forward direction reached the load, part of it will be reflected in the reverse direction, and this ratio V reflected over V incident is called the reflection coefficient, the voltage reflection coefficient. And we assume that at the load we are matched, so we didn't came to this point yet. So for now, the reflection coefficient, which is the magnitude of the reflected wave divided by the magnitude of the incident wave, does have this expression. So the total voltage or the voltage wave at any point does have this expression. Now I have a relation between V minus and V plus, which is gamma, capital gamma. So Vz can be written this way, and Iz can be written this way. So you notice that this is negative because we are expressing current in terms of voltage. So the voltage and current on the line is sort of like the superposition of the incident wave propagating in the positive Z direction, and reflected wave, which is the wave reflected in the negative Z direction. And this wave is called, like the nature of this wave is a standing wave. We're going to see why it is a standing wave. If there is no reflection, it means that ZL equals Z naught, and we say that the load is matched to the transmission line. If gamma equals 0, it means that ZL equals Z naught, and in this case it's called matched load. So it is very important to examine the amount of power traveling on this line. So the average here means time average. Power flow equal half the real part of Vi asterisk or I conjugate. So we just do the math, we can find the expression, and here this terms in blue is like a complex term minus its conjugate, and you can see that in this case this two blue curves will result in an pure imaginary term, and you are taking the real part, so they will have no effect, and they will end up with this expression here: half V plus square divided by Z naught multiplied by 1 minus magnitude square of the reflection coefficient. So the average power flow is a constant at any point on the line. The total power delivered to the load equal the incident minus the reflected. Maximum power would happen if gamma equals 0. If gamma equals 0, the reflection coefficient equals 0, the load is matched to the line. It means that the total power incident on the line will be delivered to the line, and this is the maximum powers that can be delivered. Here's this reflection coefficient. If we take minus 20, its log, then it's called the return loss, and it is expressed in dB. The return loss is a non-negative value. It can be 0 and it can be up to infinity. If it's matched, gamma equals 0, so it would be infinity. If it's like complete mismatch, as we're going to see shortly, it means that gamma equals 1, total reflection, so this will equal 0. And this quantity is called the return loss, which is minus 20 log the magnitude of the reflection coefficient. Standing wave ratio. So where is this coming from? So when we have a mismatched transmission line, we have a wave propagating forward and a wave propagating backward or in the reverse direction. So the magnitude of the voltage wave would have this expression. So we just like can express gamma as like magnitude and phase. So the voltage would have this expression, and if we calculate its maximum, it will happen when this is 0 or 2 pi, and if we calculated its minimum, it will happen when this is minus or like 180, so it will be this value. So the voltage standing wave ratio is the ratio of the maximum voltage that happened in the voltage wave divided by the minimum voltage of this wave, and this is why we are saying it's a standing wave ratio. And this quantity here is greater than 1, and it can be infinity. It would be infinity if we have complete mismatch. If we have perfect match, it would be equal to 1. So let us look here for the wave. Okay, so here this is ZL. You will find it's a complete mismatch. Here we have some mismatch. So the red is the incident, the green is the reflected, the blue is the total. So here this is a matched one. So when we have another mismatch, we'll have also an attenuation. What is the maximum, what is the minimum? If it's open, the maximum and the minimum can go like for infinity. Okay. Okay, so now we're gonna move to another concept, which is the concept of input impedance. So we know the relationship between the forward wave voltage and forward wave current, which is the characteristic impedance. Same thing for the reverse propagating voltage and reverse propagating current. We also know the load impedance, which is from the circuit theory. Now, what is the definition of input impedance? So the input impedance is the ratio of the total voltage divided by the total current at any point on the line. So if we write the expression for total voltage, again, the load is at 0. All of this is the negative L. If we write the expression for the voltage at any point, that is L distance from the load, and divided by the current at distance L from the load, and just do the math, it will equal 1 plus gamma e to the minus j beta L divided by 1 minus gamma e to the minus j beta L multiplied by Z naught. So here, like the gamma at the load is gamma 0. At any other point, it is changing its phase. So we can write gamma L, gamma at any distance L from the load, to equal gamma at the load multiplied by e to the minus j minus 2j beta L. L is the distance between any point and the load. And this is Zn, which is the ratio of the total voltage to the total current at any point on the transmission line. We can just use this expression for gamma to rewrite, or like to come up with another expression for Zn in terms of Z load and characteristic impedance. It would have this expression here, and because tan is a periodic and it is a periodic with lambda by 2, so Zn will be periodic also with lambda by 2. So if the length is x, or x plus lambda by 2 will have the same input impedance. So let us just do another example. If we have a lossless transmission line, the electric length of the transmission line equal 0.3 lambda. And as I explained in the previous lecture, electrical length means the physical length divided by lambda. So the length is 0.3 lambda. It's called the electrical length. And this transmission line is terminated as shown in the figure. Also, the characteristic impedance of the line is given in the figure. And we would like to calculate those four things: reflection coefficient at the load, the voltage standing wave ratio on the line, the reflection coefficient at the input, and the input impedance at the line. And it's very straightforward, but it does have like complex number manipulation that you need, as I said last lecture, you need to review and make sure that you are at a good like level of remembering all its details. Okay, so we just tried the gamma, reflection coefficient at load equal V minus over V plus, and it does have this expression because the load is a complex. We'll do like convert from polar to from Cartesian to polar, and we do the math to come up with the reflection coefficient. Can get the magnitude. So the standing wave ratio is 1.4 divided by almost 0.6, it will equal 2.7. The reflection coefficient at the input here, L equal 0.3 lambda. So gamma L equal gamma, which is gamma naught, this one, multiplied by e to the minus j beta L. E to the minus j beta L, of course, its magnitude is 1, its phase is minus 216. So just the multiplication, it will be the same magnitude as we know, but the phase will be different. So it would be minus 145.25 multiplied by minus 216, so it will be minus 361, I think. Yes, 361.25. We remove the 360. It will end up with this number here. Z input would equal, just substitute in the expression and we'll find its input impedance. There are like some famous special cases of transmission line termination that it is always good to go through, and we're going to do that. The first one is short-circuited terminated transmission line. So short-circuited means ZL equals 0. When ZL equals 0, we just substitute in the expression for the reflection coefficient. We'll find that the reflection coefficient equal minus 1, which is full reflection, and the standing wave ratio would be infinity. The VZ would have this expression, so it would have like imaginary constant multiplied by V naught sine beta Z. The current would be cosine beta Z. The input impedance would be pure imaginary. it's from minus j multiplied by tan beta. So it can goes anywhere from plus infinity to minus infinity. A special case of this special case is when L equal lambda by 4. In this case, Zn will equal infinity, which is like the open circuit. So the short circuit transmission line, if its length is lambda by 4, it would be seen at the input as an open circuit. And we know that the impedance is periodic with a period lambda over 2. So anything that's lambda over 4, 3 lambda over 4, 5 lambda over 4, so on and so forth, all of these cases, the short circuit will look like an open circuit. So we just see the voltage waveform. It's a sine. The current waveform is a cosine. At the load, voltage over current equals 0. After a lambda by 4, it will look like an open circuit, and things would continue repeating up every lambda by 2. So the impedance periodicity is lambda by 2. The second case of the second special case for a transmission line termination is the open circuit transmission line. Open circuit, ZL equal infinity, current equals 0. So at the load, we can calculate gamma, the reflection coefficient. We'll find it to be 1. I'm just here like explaining how to do that. The standing wave ratio will equal infinity. The voltage waveform would take the form of a cosine. The current would take the form of a sine. Z input will be pure imaginary with this format. The special case for lambda over 4, the open circuit will look like a short circuit. So if we want to implement like input impedance of open circuit, we can just make it open, or we attach a short-circuited lambda by 4 transmission line. So this is the voltage waveform, current waveform, the impedance, and the impedance is periodic with a period of lambda over 2. A third, or now it is a third special case of transmission line termination, which is the lambda by 4 transmission line. So for any load impedance, the Z input would be Z naught squared divided by ZL. So again, it would have the same value for L equal lambda over 4, or any added to any integer number of lambda over 2. This is the lambda by 2 periodicity again here, and this section in the next lecture we'll talk about it. It does have a very famous application that is called lambda by 4 transformer. We'll talk about it in the next lecture, inshallah. A fourth special case of transmission line termination, the matched transmission line. Matched transmission line means ZL equals Z naught. So the reflection coefficient equals 0, standing wave ratio equal 1. There is no reflection, all the waves are in the positive propagation. Z input is not varying, it's equal to the characteristic impedance at any point on the line. So here I would say infinitely long transmission line behaves similarly to a matched transmission line. Why is that? I would like you to think about it, and I'm going to give you the answer. I will give you the answer directly, but it is good that you pause and try to find the answer yourself. An infinitely long transmission line looks like and behaves like a matched transmission line because it's very long. So the load is at infinite distance from any point. So any waves that goes, it will keep going, keep going, keep going. It will keep going forever before reaching the load. So no reflection will happen. It will be very similar to the behavior of matched transmission line, where the current does have a single component propagating in the positive Z direction. Matched cause no reflection. Infinite long cause no reflection because the signal will take forever to reach the load, theoretically speaking. Another important parameter for transmission line, that is the insertion loss. So consider like two sections of transmission line, section 0 and section 1. They have different characteristic impedance, and those two sections are connected like in series to one another. The amount of power that goes from section 0 to section 1 is called the transmitted power. So at this point, some of the power will be reflected, some of the power will be transmitted. Insertion loss is related to the transmitted part, and return loss is related to the reflected part. So here the right part, the part number 1, is infinitely long, so it's actually acting as a matched load transmission line. So just write the voltage for section 0, the total voltage for section 0. It would equal the plus e to the minus beta z plus the reflected wave, and this is happening in section 0. We assume this interface to be at z equals 0. Gamma will equal z1 minus z naught divided by z1 plus z naught. And I'm asking you why. You pause the signal, you pause the video, try to think about the answer, then continue. So the idea here, because this is infinitely long, so it acts as a matched transmission line, which means that the input impedance at any point equals Z1. So for section 0, section 1 is the load, and the load impedance is the input impedance to Z1 because it's matched or infinitely long. The load impedance to section 0 is the input impedance to section 1, which is the characteristic impedance of section 1, which is Z1. And that's why this is the expression for the reflection coefficient. V1 is the wave on section 1 that is propagating in just the positive Z direction, no reflection because it's infinitely long. So it does have this expression, and we would like to know the ratio between V1 plus divided by V0 plus. This ratio is called the transmission coefficient. Taking the log of this transmission coefficient is called the insertion loss. So the definition of insertion loss and definition of return loss are very important in transmission line applications. So we're dealing with this dB, and in engineering we frequently deal with this dB quantity, just to have like a wider or like more sensitivity to a wider variation length. So if we are talking about the ratio of power, it will be 10 multiplied by log. If it's a ratio of voltage, it will be 20 multiplied by the log. There is another quantity which is the neighbor for it's the natural logarithm for power. It's half ln for voltage, it is the ln, and you can say that 1 neighbor equal 8.68 dB. the decibel and bar are frequently used in microwave engineering and in engineering in general, but in our case they are very useful. Why? Because if we are cascading a number of sections, for example, like if we are cascading two amplifiers, first amplifier amplifies by a certain value, then the second one amplifies with the other value. If we are using dB, so the effect of the two amplifiers would be the sum of dB of amplifier 1 and gain of amplifier 1 plus the gain of amplifier 2. Same thing if we have multiple sections and we have attenuation on each section, the total attenuation would be the summation of the attenuation of those sections. So that's why, like many times, the dB is really useful. Also, we can use the dB in expressing absolute quantity if we are referring to a specific known value. For example, if we are referring the power to the milliwatt, we can say that this power 1 equal dBm. Like, what is the meaning? It means that its ratio to 1 milliwatt equal certain number, or if it's referred to watt, so it would be like dB watt, so on and so forth. So it is useful and frequently used in microwave engineering this way. There will be a homework, and the homework is after 1 week from the discussion session. I will post the homework on the Google Drive and wait for your submission of the homework in a week. At the end, this is a summary of the learning objectives. What did we learn in this lecture? So what I want you to do is just make sure that you understand all of this by the end of the lecture. Thank you, and meet you in the discussion session. Goodbye.